Hello everyone, welcome to Chapter 3, Probability. We continue with our lectures on Chapter 3. Here my focus would be on mutually exclusive events, independent events, counting principles, and formulas related to that. Let's start with mutually exclusive. Events. Again, in English, you probably can figure out what this means, but let me define it for stats. These events cannot occur at the same time. That is what we mean by mutually exclusive events. Okay. So, for instance, if I said a nursing student and a male student, are these two mutually exclusive events? So they're asking, can these two events occur at the same time? Can a nursing student also be male? And we say, yes, that's possible. That can happen, right? So that means these two events are not mutually exclusive. On the other hand, if we say an athlete is both riding the bike and the athlete is also swimming at the same time. The athlete is riding the bike and swimming at the same time. Can this be possible? Can these two events occur at the same time? Okay, very skeptical, right? It's maybe someone will try and dare it to do, but generally speaking, you can't ride your bike and swim at the same time. Say, for example, if he's a triathlete. Okay, so we have examples like that to show that if two events cannot occur at the same time, that is, those are mutually exclusive events. Another example would be a professor being present in two offices at the same time, right? Two physical offices. Don't tell me you can zoom in and be in two places at the same time. What I mean here is having the presence maybe in an office and in a classroom at the same time or something like that. So the probability notation for this would be that probability of event A and event B occurring would be 0, 0. That means no chance. There's no way, absolutely no way that this can happen, right? So the event cannot happen if they are mutually exclusive events. A and B would be, probability of A and B would be 0. If you were thinking in terms of Venn diagram, right? Remember the diagram I discussed in the previous lecture? So in the Venn diagram, if you were having overlapping rings like this, nothing would be no common element. There'll be no common element in the overlap region just because they are mutually exclusive events. They do not share, which implies no shared outcomes for A and B. So let me call this A and this as B. That means we're saying A and D would not have any element that is common here. So it's as if you had elements here, 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 and you had something else here, 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 but nothing in common there. Now, how do we know if it is mutually exclusive or not? If it is not explicitly stated to us, then we have to assume that they are not, okay, until you can show it otherwise. So we'll take a look at an example here. So you have a fair, well-shuffled deck of 52 cards. It consists of 4 suits, clubs, diamonds, hearts, and spades. There are 13 cards in each suit, consisting of 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace of that suit. Given events A and B are, given that events A and B are these two mutually exclusive. So event A is choosing a Jack, event B is choosing a card in the spade suit. Okay. So then, I mean, some of you can already see what this is, but let's describe event A. A is choosing a Jack. Okay. So we can have Jack of, we have those 4 suites, right? So we have Jack of clubs, Jack of diamonds, Jack of hearts, and Jack of spades. And even B is choosing a card in the spades suite. So then you have 2, 3, 4, 5, 6, 7, 8, 9, 10, and Jack. This is all these are spades, so I'll just put the S there just for emphasis. All right. So now we have to figure out if A and B are mutually exclusive events. We just established that if they're mutually exclusive events, they cannot occur at the same time in both these events. Right? That means there cannot be any overlap. But what we do see is there is an overlap here. Jack of spades is found in both A and B. So what do you think? Do you think these are mutually exclusive events? No, they are not mutually exclusive events because they share a possible outcome, which is the Jack of spades. You say no, A and B are not mutually exclusive events. We can say as they share a common outcome. Outcome Jack of spades. Okay. Now let's look at another example. Okay, same scenario. So we'll just skip to the events A and B. Event A is choosing an 8 and event B is choosing a Jack of hearts. So let's go ahead and do A. A is choosing an 8, which means it can come from any one of the 4 suits. So you have 8 of clubs, 8 of diamonds, 8 of hearts, and 8 of spades. And event B is choosing a Jack of hearts. Very, very specific. Jack of hearts. There's only one such Jack of hearts. So we have only one element in B. So look at A and B. Do they share anything in common? Clearly, there is no overlap, nothing in common. Therefore, we can say that A and B are mutually exclusive events. So let's say yes, A and B are mutually events, exclusive events, as they do not share any common outcomes. So you can say no overlap, right? And if you were to show this in the statistical notation, so we say probability of A and B is equal to 0. Now we saw in the addition rule that probability of A or B is probability of A plus probability of B minus probability of A and B. This was assuming that A and B were not mutually exclusive, meaning they had some overlap, so you had to remove the overlap. But if you had A and B to be mutually exclusive events, then you see that your formula reduces to simply probability of A plus probability of B, right? Since probability of A and B would now be 0 if they were mutually exclusive. So we want to keep that in mind. So let's take a look at this example. Event A has these outcomes, B has those, and C is given to be those. And we are asked to find P of A or B. I've also shared with you the Venn diagram to see how this information can be represented. Okay, the Venn diagram is a whole lot easier to visualize this because you can see all the overlapping elements there, and so it really helps to see what values really overlap and between what two sets or events you see the overlap. Well, we will begin. This is just a visual representation, so if you don't have the Venn diagram, you can still do this because you have A, B, and C listed to us. So I want to find the sample space. What are all the possible values that are provided to us in this problem? So it is all of the things that are contained in A, B, and C. So we have 1, 2, 3. 3 comes from set C, right? 3, 4, and 5 is from B. 6, 7, 8, 9, 10, 11, 12. So we have 12 elements here. There are 12 possibilities. And A is given to have four of them, right? And we are asked to find probability of A or B. That means we want to take all of A and all of B, right? That's what we would do. Typically, that's what we did before we were introduced to the addition rule. So A or B would be 1, 2, 4, 5, and 5 repeats here, so we'll skip that. 6, 8, 9, 10, 12. Okay, but we are going to use the addition rule, probability of A or B. So I'm going to do P of A plus P of B minus P of A and B. Okay. So P of A, how many elements do we have in A? 1, 2, 3, 4. So it's 4 out of 12. And B has 1, 2, 3, 4, 5, 6. 6 out of 12. You can reduce that to 1 over 2, but I want to keep the same denominator, so I'm just going to keep it as out of 12. Now we need to find P of A and B. So I'm going to do it up here. Okay. A and B means what overlaps only between A and B. So I find only 5 to overlap between A and B. So we'll just, probability of A and B would be 1 out of the 12. Right? Minus 1 out of the 12. So if you compute this, because they have the same denominator, you can simply add the numerators. That gives us 9 over 12, right? And that reduces to 3 over 4. So this is using your addition rule. Here you notice that P of A and B gave you a number, which means A and B are not mutually exclusive. That means you found something that was common. In fact, we found 5 to be common, right? If you didn't find anything common, that would become a 0, indicating that A and B are mutually exclusive events. So now if you did the old method where we just directly listed how many we had, that would 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that would have given us that same 9 out of 12, which is 3 over 4. Probability of A or B directly would have given us this. But in this formula, we use the P of A and B to eliminate any extra or any duplicate counts of the value in A or B. All right. Claus is trying to choose where to go on vacation. His two choices are A, New Zealand, and B, Alaska. Claus can only afford one vacation. The probability that he chooses A is 0.6. The probability that he chooses B is 0.35. What is the probability that he chooses New Zealand or Alaska? Okay. So A is New Zealand and B is Alaska. We're told probability of A is 0.6 and probability of B is 0.35. So this is New Zealand and this is Alaska. Now, if you take the question, it says, what's the probability that he chooses New Zealand or Alaska? You see the word or, we're using the addition rule. That means probability of New Zealand plus probability of Alaska minus probability of New Zealand and Alaska. I want to convert this to the A and B that's given in the problem because that is how you should always define. So that's the same as P of A plus P of B minus P of A and B. So what's the chance of him going to New Zealand and Alaska? So think about it. If you go back, it says he can only afford one vacation. So he can't go to both these places. So very clearly, this implies P of A and B should be 0 since Claus can afford only one vacation. This implies A and B are mutually exclusive. So if you come back here, probability of A or B would be simply reduced to probability of A plus probability of B. And then you can simply plug in your values, 0.6 plus 0.35. Which is 0.95. That's cool. So our question was, what is the probability that he chooses New Zealand or Alaska? And the probability is 0.95, indicating that there is a 95% chance that he will choose to go to either New Zealand or Alaska. Now let's talk about independent events. You know that mutually exclusive events means the two events cannot occur at the same time. Independent events is that the probability of one occurring does not affect the probability of the other happening. Let me write that information here. So A and B are independent events if the probability of one occurring does not affect the probability of the other happening. Well, I just wanted to observe here and make a quick note. You might have seen already now that I write and explain what I write. I kind of read what I write, and as I write, I read. I do all these things just to accommodate students who have low visibility or who may have other disability, wherein me reading out the question as I'm writing, or if a question is presented already, then I read out the question just so that I can accommodate those needs as well. So if some of you are feeling a little impatient that I'm doing that, please bear with me. I want this course to be a positive experience for all learners as much as possible, as much as humanly possible for me. And so that's something I want to let you know as well. Okay, moving on. What we see here is we have something called multiplication rule. We have the addition rule, right? Like that, we have multiplication rule. And according to the multiplication rule, if we have A and B are independent events, okay, if they're independent events, probability of A and B would be probability of A times the probability of B. That's why it's called the multiplication rule. Okay, I want you to really understand this closely. If A and B are mutually exclusive events, they both cannot occur at the same time, then the result is 0. P of A and B will be 0, as what we saw before. But if your A and B are independent events, and by definition, we're saying the probability of one occurring does not affect the probability of the other occurring. Right? So if you're flipping a coin and rolling a die, they are independent events because rolling a die or flipping a coin, the probability of rolling a die does not affect the probability of flipping a coin. Right? They do not have impact on each other. And so it's those kind of events where P of A and B would be P of A times P of B. In fact, we've done this kind of thing in our fundamental counting principle. In our fundamental, think of those ice cream examples and the pizza examples. There, what we did was we took the probability of the first process times the probability of the second process times the probability of the third process, and so on. So we could clearly see that the number of scoops in that ice cream example the probability of the number of scoops did not impact the probability of the flavor of the ice cream, which in turn did not impact the toppings of the ice cream. So they were three independent processes. They were three independent events. And therefore, what we did was we multiplied their probabilities, right? So in the tree diagram, we did those problems. So I want you to remember that it's all connected in that sense because A and B are independent events here. That's what we see it as. There are two known potential defects on a certain brand of a computer. Let A be the event that the keyboard malfunctions and B be the event that certain types of memory will randomly erase. The probability of events A and B happening is 0.54. If A and B are independent events and P of A is 0.9, what is P of B? Okay, let's collect the information we have. A is keyboard malfunctions. And we are given P of A to be 0.9. B is, I'll just say memory erase. P of B is not given to us. I put a question mark there. And we're told A and B are independent events. Again, I want to highlight here, not to confuse with the mutually exclusive. Mutually exclusive means those two cannot happen at the same time. Here we have keyboard malfunction and memory erase. These two can happen at the same time. Not a problem, right? You can have these two errors happening. But A and B are independent events, which means the probability of the keyboard malfunctioning does not affect the probability of the memory erase. Okay, so in that sense, they're independent events. We're told P of A and B, probability of events A and B happening is 0.54. So now we are, because A and B are independent events, we use the multiplication rule, which says probability of A and B is probability of A times, get that there, probability of B. So A is 0.5, A and B is 0.54, A is 0.9, and you have to find probability of B. So mathematically, you want to isolate P of B. So you divide both sides by 0.9, and you get P of B. That's 54 and 9, right? So that's a 6, so it's a 0.6. So we got a probability that the memory will erase randomly is 0.6. But I want you to pay attention to how you can modify this given formula, right? P of A and B is P of A times P of B is the multiplication rule when A and B are independent. So this implies if you wanted P of A, and if you're given P of A and B and P of B, then you divide both sides by P of B and the formula becomes this. And what we just saw was that we could find P of B by dividing both sides by P of A, and your formula would look like this. So remember, the variations are all mathematical possibilities, so you're expected to know how to rearrange these terms to create these variations. Okay? So let's say I give you another problem where A and B are independent events. Probability of B is given to be 0.3, and probability of A and B is given to be 0.15. Find P of A. So you can recall this variation and say P of A is P of A and B divided by P of B, and plug in those values. Which is 0.5. Now, if you wanted to change this to a decimal and give it as a percentage, you multiply by 100%, so you get 50%. So there's a 50% chance for event A to occur. Yeah. So we saw multiplication rule for independent events. Here we're going to talk about multiplication rule for conditional probability. So let's quickly look at what this means, the conditional part. As the name says, there is some condition upon which it rests. Okay. So conditional probability means that we find the probability of one event based on the probability of another event that already occurred. Okay, so let me write that down here. So there is a condition there, right? So I can give you an example for that. Let's say a person misses their connecting flight, given that their original flight was late. So that's an example of a conditional probability where the original flight was late, that event already happened, right? And based on what already happened, we're trying to find the probability of the next event. So in this case, the person missing the connecting flight, given that the original flight was late, shows you that sequence of events here that happened, right? So the formula here would be, or at least the notation here would be, if I say probability probability of event A given that event B already occurred is written by P of A, a vertical bar B. Okay? That is A given B. That's how you read it. So the probability of A given B is given to be probability of A and B over probability of B. Okay, probability of A given B. So let me point to that here. Probability, I'm going to write it in words, of event A given event B already occurred. Okay. Now, if I switch this around, okay, and I said probability of B given A, you know that they're not the same, right? Because we switched the order of events, so it's not the same. So if I went back to the airplane example, we said the person missed the connecting flight because the original flight was late. If you change the order, won't that be absurd? Because it'll be that the person took the connecting flight first and then took the original flight. It's even meaningless for me to explain it that way. But I hope it drives home the idea that you can't switch the order and assume things are going to be the same. No, sometimes they just are rendered meaningless because you change the sequence of events. So this is really important. Now, if it's B given A, the formula would be P of A and B, or B and A. Right? Doesn't matter the order there. But it's going to be divided by P of A. And here again, I would like to give the explanation that this is the probability of event B given event A already occurred. I'm going to use this green expression as the example to derive other ways to other variations to this formula. So if you're given the P of B given A and you're given P of A, you can find P of A and B by rearranging the terms, which will be P of B given A times P of A. Okay. And likewise, you could also find P of A, which is P of A and B, over P of B given A, just to see if you can mathematically rearrange the terms. Okay? All right. In this example, the probability that a randomly chosen student plays in the band is 1 over 50. The probability that a randomly chosen student sings in the choir and plays in the band is 1 over 200. What is the probability that a randomly chosen student sings in the choir given that the student plays in the band? Okay, I know it can get a little overwhelming, even confusing. So let's first write down what we have. Okay, I'm going to write it in by removing the clutter. So probability of the student who plays in the band. Okay, is 1 over 50. The probability is a student sings in the choir and plays band is 1 over 200. We have to find what is the probability that a student sings in the choir given that the student plays band. We had to find this. Now, to make it a little easier on us, I'm going to call the student who plays in band P, plays in band P. Student who sings in choir will be S, sings. So again, remember, we're trying to assign letters to define the events. The two events that are happening here are playing in the band and singing in the choir. So these are two events. Therefore, using these two, I can come back here and say plays band. So S given P would be this. Sings in choir and plays band would be S and P. So I want to come down here and write it out. So P of P, first one, is 1 over 50. P of S and P is 1 over 200. We're asked to find P of S given P. Now, let's take a look at our conditional probability formula. Okay, how do I know it's conditional? Well, there are many clues. Let's see this word given that. Given that usually tells you that they in the problem that they are talking about conditional probability. So that's how you can even write this as S vertical bar P, right? So conditional probability says probability of A given B is probability of A and B divided by probability of B. So I'm going to translate this for our problem that uses S and P, right? So we're supposed to find probability of S given P. Make sure you put the players in the right spot. So probability of S and P given probability of P, right? Now that I've assigned them the right positions, probability of S and P is given to be 1 over 200 divided by probability of P is 1 over 50. This is where you will use math concepts. This is a fraction over a fraction. It's called a complex fraction. The way we do it is we write the first fraction as it is, the numerator, times the reciprocal of the denominator. Reciprocal means to flip the denominator. So times 50 over 1. Okay. And if you would reduce this, 5 times 1, 5 times 4, you can use your calculator, but that's going to give you a decimal answer, and we want fractional answer. So, cross-canceling is the way to go about this. Your answer would be 1 over 4. So then, if you were to answer this question, the probability that a randomly chosen student sings in the choir, given that he or she plays in the band, is 1/4. Let's talk about replacement. What happens in conditional probabilities is that the idea of replacing a subject that was used in the drawing can change the sample space. So to give you a clearer picture of this, I'd like to use a deck of cards, playing cards, as our example. Okay, so if you are drawing a card from the pack of cards, if you're drawing a card from a set, from a deck, and if you would put back that card before drawing the second card, we call that with replacement. Okay. Now, if you are instead drawing a card from the deck and putting it aside, you don't replace it before you pick the second card, then we realize that that's going to change the sample size, because originally in a standard deck we have 52 cards. So if you removed one card and did not replace it, the deck of cards is now reduced to 51. So you see that the sample size changes. And so it's important that we understand with and without replacement concepts. So I'm going to write those details here. Under with replacement, I'll say, if events are happening with replacement, an item from the population is chosen, again think of our example, drawing a card from a deck, okay, and then replaced before a second card or second item is chosen. Here the sample size does not change. So we have 52 cards in the deck. You pull one card out, you replace it, and then pull the second card. There was no change in the sample size. Now when we talk about without replacement, the first item is chosen but not replaced before a second item is chosen. And we see that here the sample size changes. Check out this example. A bag of candy contains 3 blue candies, 4 green candies, and 6 red candies. If you draw 2 candies, one at a time, and without replacement, what is the probability that you will draw a green candy and a blue candy? Okay. So first of all, the big clue is that it says without replacement. To again organize this information, I'm going to call G as the event of drawing a green candy. It's done one by one, right? It says 2 candies are drawn one at a time. So you draw a green and a blue. Drawing a green candy in the first draw. And B will be is the event of drawing a blue candy in the second draw. So the second draw is conditioned upon the first draw, right? Therefore, the probability of B and G is the probability of drawing a green so probability of B given G would mean that green is drawn first, followed by the blue, right? So that will be the probability of drawing a blue candy, given that the first candy was green. And then we have, so right there you see the condition because of the order in which it happened. Then probability of G and B would be the probability of drawing a green candy and a blue candy. And so we're asked to find this information, right? What is the probability that you will draw a green candy and a blue candy? So this is what we're asked to find. So then let's go and understand probability of each one of them. First, for that, I'm going to first write the formula. Probability of B given G is probability of B and G. Remember, B and G is the same as G and B. So we're fine there. Divided by probability of G. So if I want to find probability of B and G, I have to rearrange this so that I get probability of B given G times probability of G. So now remember, green is the first one we're drawing, right? So let's go back and look at the question again. So there are 3 blue candies, 4 green candies, and 6 red candies. Okay, actually we didn't use the red anywhere. That's fine. We're going to need that because that will be part of our sample space. So let me write out here. The sample space is 3 blue, 4 green, and 6 red candies. So the outcomes would be 3 plus 4 plus 6. So we have 13 outcomes. Totally, there are 13 possibilities, right? So when we are drawing the first candy, you have all 13 in the, what was it, bag? Yeah, in the bag. So we have all 13 candies in the bag. So that, therefore, probability of picking a green candy in the first draw is, how many greens do we have? We have 4 greens, right? We have 4 green candies there. So you can choose any one of those greens. So we have 4 possibilities, desired green candies out of the total 13. Right? Now we have to find probability of B given G. If you go back to the problem, it says that we are drawing 2 candies one at a time without replacement. So the first time you pulled a candy and that was a green, you've set it aside. So now in your bag, you no longer have 13 total candies, you have only 12 of them, right? And within these 12, out of these 12, you want to draw a blue candy because this is the second draw. And if you look at that, there are 3 blue candies because we didn't draw any blue yet. So all the 3 are still available. So it is 3 blue candies, right, from here, out of the 12 that's remaining, because we have the without replacement condition, which reduced or changed the sample size. That is really, really crucial, right, when they said without replacement, because it changed it. If it was with replacement, if we put that green one back inside the bag, then it would have been 3 out of 13. But now that's changed. Now we're ready to plug this in the formula. Probability of B and G would be this 3 over 12, probability of B given G, times the probability of G, which is 4 over 13. So again, you have to give your answer as a fraction. So I do the cross cancellation here. So that gives me 1 over 13. So the answer here would be 1 over 13. In this example, the probability that a student is an accounting major and in a statistics course is 0.3. Probability that a randomly chosen student is in a statistics course, given that the student is an accounting major, is 0.7. What is the probability a student is an accounting major? Ooh. Okay. So what I'm going to do is, because it's too wordy, I go around looking at the events. So the event is that a student is an accounting major, the student is in a statistics statistics course. So accounting major, I'll call it A. Statistics course, I'm going to call it S. Okay. So now let's say probability, the student is an accounting major and in a statistic course, A and S is 0.3. The probability that a randomly chosen student is in a statistics course, so S, given that the student is an accounting major, is 0.72. Right there you have the big clue, right? Given that. That means you're using conditional probability. So you bring that bar, that vertical bar, when you have the conditional situation. And then they're saying, what's the probability that a student is an accounting major? What is this? So let's go ahead and put the formula for conditional probability. Probability of S given A is probability of S and A divided by probability of A, probability of what is given. Right? We're asked to find P of A. So rearrange the terms. So this implies P of A is probability of S and A divided by probability of S given A. Cross multiply. Now we're ready to plug in the values. So S and A is 0.3. S given A is 0.72. Because these are given to you in decimals, you're free to use the calculator. The answer is 0.416666, etc. You usually put a bar above it, right? But I'm going to round it to 0.417. And that's your answer. Okay. So the conditional probabilities really help us understand how the sequence of events can have an impact. And what happens if you have a conditional probability and those events are independent? Okay, let's see what happens. So we've seen previously, let me write it here, conditional and independent. You've seen this combination. Now, conditional and mutually exclusive was that P of A, there was no conditional actually. A and B were mutually exclusive, was P of A and B equals 0. So let me write that here. Is 0 if A and B are mutually exclusive events. That means they cannot occur at the same time. But we saw that P of A and B is actually P of A times P of B if A and B are independent events. So please make this distinction, okay? So if A and B are independent, then you'll see that the formula probability of A given B is probability of A and B divided by P of B, it's always divided by what is given. This would reduce to probability of A given B. Now P of A and B can be replaced by P of A times P of B, right? Divided by P of B. And this allows you to cancel off those two matching probabilities. So interestingly, when the conditional probability happens on independent events, it's simply P of A, meaning it's as if it didn't matter if event B occurred or not. And that makes perfect sense because they're independent events. The probability of one event does not impact the probability of the other one. Therefore, probability of A given B is the same as P of A if A and B are independent. Likewise, probability of B given A is the same as probability of B because it doesn't matter if A happened before it, because these events are not dependent. Yeah. So think of that plain example, right? So the plain example was the person missed the connecting flight given that his original flight was late. There you see the connection, right? They are dependent. So the sequence of events matter. If they are independent, then it doesn't matter. So what it means is the person missed the connecting flight given that he is wearing a green shirt. It doesn't matter, right? Because they are independent events. Him wearing a green shirt has no impact on him missing his connecting flight. So you want to really see that that is what we're trying to highlight here. Okay. So you'll have problems based on this condition where they will say, can you determine if these are independent or are they dependent and so on. Okay. Given the following information, what can we say about the relationship between events A and B? P of A is 0.21, P of B is 0.53, and P of B given A is 0. Okay, so this is a question where they're asking us to find the relationship between A and B. That means they're asking us, do you think A and B are mutually exclusive or are they independent? Or are they dependent? That's another option, right? All right, so we want to first establish this. Okay, we've seen this before. Let's write it one more time. Probability of A and B is 0 for mutually exclusive events, and P of A and B.
I'm sorry.
Probability of A and B is probability of A times probability of B if they are independent events. So I want to combine these two. Probability of A and B equals P of A times P of B, right? If this is equal to 0, what does it mean? This means, from again algebra, if you multiply, this is called the zero factor property that you learned in intermediate algebra. If you had two factors multiplying that are set equal to 0, then it means one of them is 0. Right? So let me write it. If A times B equals 0, it implies A is 0 or B is 0. That's the only time that it can be 0, right? So if A is 0, 0 times B will be 0. If B is 0, then A times 0 will be 0. So that's the same idea I'm extending here. So this means P of A equals 0 or P of B equals 0. Right? So we want to understand that to answer this particular question, what we have here is P of B given A. Okay? P of B given A would be P of B itself, right? If A and B are independent. We saw that before, meaning that it doesn't matter if you were given the sequence of A occurring first. It doesn't matter because they're independent. So we can check that here. So we are given P of A to be 0, A given B to be 0, P of B to be 0.53. They are not the same. If they were the same, A and B are independent. So this establishes that A and B are dependent. They're not independent. Okay? That's the relationship between A and B. Are they mutually exclusive? Okay. So for that, if you come back here, once again, P of B given A equals 0 means that if A had occurred, then B cannot occur. Right? That's what this means. A had occurred, but the probability of B, given that A had occurred, is 0. That means B did not occur. So A occurred, B did not occur. Let me write that. This implies A occurred, but B did not occur. I know B did not occur because the probability gave me a 0. 0 means there's absolutely no way it can happen. So A has already happened because we know that from the given condition. B given A means A already happened. So A happened, but B did not happen. And what is the definition for mutually exclusive events? It says that both A and B cannot occur at the same time. So this is a clear example where one occurred and one didn't. So this implies that A and B are mutually exclusive events. I hope this drives home the idea very, very clearly, because you don't automatically assume that they're independent, therefore they're mutually exclusive, or if they're mutually exclusive, they're going to be independent. No, here's a case where these were mutually exclusive events which were dependent. Now we talk about counting principles, and we have different ways of counting. We've already seen the fundamental counting principle. We also have permutations, combinations, and a special case of the fundamental counting principle, which would be a factorial. I'm going to work on these one by one, quickly explain them, and then we'll go into examples of them. Now, the fundamental counting principle, if you recall, we did A times B times C. If there were three events that occurred, A would be the number of possibilities or number of outcomes in A, number of outcomes in B, and number of outcomes in C. We multiplied them out. Okay, and this again would work if they were independent, right? If they were dependent, that's going to change. We'll look at examples on this, but this was a fundamental counting principles. It helps us to count the total number of outcomes. And a quick way to remember this was our tree diagram. We said we cannot draw the tree diagram every time because it becomes really, really large for some multiple options, and therefore we can use the fundamental counting principle to overcome that challenge. Okay, and I'm going to go quickly down here to number 4. What happens is sometimes when you are multiplying the numbers A, B, and C, let's say you had 4 times 3 times 2 times 1, something like this. Okay, you had a sequence that looked like this, wherein there were 4 processes, 4 events. Now, the special case here is that it reduces by one number each time, right? 4 times 3 times 2 times 1. This can be represented by a special symbol which looks like 4 and an exclamation mark. We call this the factorial. Okay, n factorial. Read as n factorial. So you don't say n exclamation mark. Okay, you call it n factorial. So in general, n factorial will expand as n times n minus 1, 1 less than n, 1 less than n minus 1, which will be n minus 2, etc. 3 times 2 times 1. So that's how it ends. So 5 factorial would be 5, which is your n minus 1, so 1 less than 5, which is 4, 1 less than 4, so that is going to be 3. Or if you see as n minus 2, that is 5 minus 2. So maybe I'll just try to expand it here for you, just for the formula's sake. Five minus 4. We're not going to do 5 minus 5 because then that will be a 0, right? You can stop when you reach 1. So that's going to be 5 times 4 times 3 times 2 times 1, which is 120. So we're going to say that there are 120 ways or 120 possibilities for something. Okay, so a factorial could be a special case of your fundamental counting principle when you multiply and it lands up in a sequence like that where it's 1 less. Now, also I want you to remember that 0 factorial is 1. So here, even if you went further and did 5 minus 5, it doesn't hurt us when we do it as a factorial, but it hurts us when we do it as a product, right? So that's the reason why we don't do that. We stop with 1, but 0 factorial is considered as defined as 1. Now let's talk about permutations. Permutation is a way of arranging a set into a particular order. Okay. Write that there. So what this means is, say you had a set A, B, and C. Okay, there are three elements there. Okay. A, B, and C. So if you're using the fundamental counting principle, there are three ways of arranging this, right? The first one is 3. You have 3 numbers. Okay. Then you have only 2 left, so you'll have 2 numbers. Then you have only 1 left, so that's 1, which is basically your 3 factorial. So we have basically 6 permutations, we say. So if you were expanding this in your sample space, okay, what this means is that you will have A, B, C as one way to arrange it. Then you have A, C, and B. B, A, C. B, C, A. And then C, A, B. And C, B, A. Okay, so you have those 6 possibilities there. So we are trying to arrange this in a particular order, right? Notice that, for instance, A, B at C, and let's say C, B, and A are 2 permutations, 2 arrangements, even though they have the same elements. Okay. So in other words, the order does matter here, right? The order makes a difference. So order does matter for permutations. Okay. It's got a special formula as well. Okay. And the formula for that would be NPR, which is n factorial divided by n minus r factorial. Okay. So this is a formula you will use when you are trying to find the number of ways to select r items from n items. Where the order does matter. Right? So you can actually expand it manually, which is not really desirable. But you have all these functions available to you in your calculator. Okay. So if you actually, choose the right key here, okay, I'll just share that with you. So in your graphing calculator, you will click on the Math button. In your calculator, go to the Math button. Okay, that's just below the alpha, the green button. This is TI-84 plus. So in the Math, when you click on the Math button, it takes you to 4 tabs. There's a Math, Num, CPX, and PRB. Go to the PRB, that's a probability tab. Okay. If you go there, and if you go to the second option in the menu, it shows NPR. Okay. So in order to use that, you'll have to first enter the N, and then go to the Math button, reach that PRB and the NPR option, and then enter the R. So you can't, you have to do a number before that using that key, and then enter the R after you use the key. Let me do some examples. I can show that to you. Okay. So it's kind of easy there. And you can also find your factorial key. If you wanted just the factorial, that can be found as well. And you can directly do the factorial. But for this one, we just want to use the PRB and the NPR directly. But if you go to math, same thing. Right there where you are, you notice that the fourth option gives you the exclamation mark. So that is your factorial option. If you want to do it manually, but you want to use a calculator to compute the factorial individually, you can do that. Or you could use the you could use the second option, which is NPR. Like permutations, combinations also an arrangement. Here we are doing a grouping of items in a set where the order does not matter. So think of that ABC. Okay. So we have 3 elements in this, and we want combinations of 2 elements. Then we say, okay, we can choose AB, AC, and BC. Okay. Meaning you are not creating another option which is C, A, because if order mattered, that would be another possibility, right? That would be permutation. But in combination, this is all eliminated because order does not matter. So which means this implies A, B is considered to be the same as B, A, unlike permutations. Okay. So the formula for combinations is NCR, which is n factorial over r factorial times n minus r factorial, where here you're finding the number of ways to select r. Select r items out of n items, where order does not matter. And you can find this again in your calculator. Go to Math, go to the PRB tab, and choose the third option. It says NCR. Once again, you have to enter the n value first. Then go to this NCR button, and then enter the r value. Okay. And then, of course, we saw the factorial. So with this, we'll wind up with this lecture here. And in the next video, we will finish off with Chapter 3 with examples for all these combinations, these counting principles and probability related to that in the next video. And then that will help us to complete Chapter 3 topics. I hope you enjoyed this one. I'll see you soon.